Alrighty, here we go. So, number 10, and then we'll do number 3. Is it possible you to travel car enough? But, I know it's been a while since we did problem sets, but you are not required to pay attention, but at least don't be a distraction to me or others. Right? Some of you are just being a little bit distracting, so. Alright? I think I'll let you answer part A on your own. Alright? You're welcome. Part B. If you fly a rocket at 0.99C for 1 year, according to the ship's clock and calendars, how much time elapses on Earth during your 1 year trip? Alright? So, 1 year for 1 year according to the ship's clocks and calendars. So I'm assuming that they want to know how much time elapses on Earth from the Earth's frame of reference, right? Because it doesn't say something like, how much time do you measure passes on Earth? So I think through their verbiage, they're assuming that the measurer is on Earth. So, and then let's see what part C is. If you were 26 years old when you left home, your sister was 21, what age when you return? Will your sister's age be when you return? Those, I think, are pretty straightforward. They follow from B. So, this is problem number 10. And I'm going to start off, of course, what's our overarching factoid that makes all this happen? Speed of light is constant for all frames of reference. So, all frames of reference. And so, less time passes on the ship. Oops. Usually spell ship with SH. From Earth's frame of reference. Because I think they're not stating in the problem, but we're left to assume is the ship goes out for like half a year and turns around and comes back for half a year. Alright? So that the Earth becomes the primary frame of reference. And make these pens less. So, yeah, I think that's all you need for the Y. Any questions on the Y? Let's go to the how then. And I need some valid physics equations. So I can get those here. I'm dealing with time. So I'm going to use my time. And then I'm going to need my Lorentz transformation to go along with that. And so I'm going to just write those. So T equals T naught over gamma. I'm also going to remind myself that gamma is always greater than 1. Right? Because, so which one is greater, T or T naught? Let's go here. T naught is always greater. Divide by a number bigger than 1, you get a smaller number. See what? That's why it's good to stop and think about it. So I'm going to kind of below this just remind myself that T is less than T naught. Because that also reminds me, if less time passes on the ship's time is T, and the Earth's time is T naught. So I'm trying to link my understanding with how the math works. And then my Lorentz transformation from my equation sheet, I just tend to put one little flare on it. I write it like this. I group those together. That's something I tend to do. So, I know that 1 year passes on the ship, and T, this must be the ship one. This must be the ship. Less time passes on the ship, and that would make this Earth. And they asked me how much time passes on Earth. Right? I think that was the question. 0.99C, 1 year. Yep. So now it's really plugging in. 1 year equals T naught over 1 over the square root of 1 minus 0.99C over C quantity squared. And nicely, because I left the velocity in terms of C, that just cancels out. Yay! And then you can do I think you can do parts C and D by adding and subtracting and birthday candles and things like that, probably. Thank goodness someone was paying attention. Thank goodness. That would have been bad.
Oh.
That would have been really bad.
Does it still have the same result?
I looked at length, and I did. Yeah.
Also, it wouldn't have the same result?
We'll have to get rid of all of this. Thank you, Josh. So this would be Earth, and this would be the ship. Right? And so we do T equals 1 year over the square root of 1 minus 0.99C over C quantity squared. Josh to the rescue. And I got 7.09. All right, number 3. An unstabilized sub decays in 29 seconds when it rests. How long does it take to decay when it moves at a speed of 0.75 C? Now, I'm assuming they're saying how long does it take from outside, because if you were in its frame of reference, it would still take 29 seconds, right? But from the outside frame of reference, is it going to take more or less time? More time. More time from the outside frame of reference. So, we'll go here. Just like the last one. C is constant. All frames of reference. More time will pass in outside a non-moving frame of reference than in moving. I think it's worth saying do they tell us what type of particles they are? Isotopes. In the iso frame of reference, only 29 seconds pass. Right? I think that kind of brings it into focus on the problem itself. Remember, you've got general ideas, showing your understanding, and then explaining it. Get your room back to the how is right in here. All right. Same exact equations as last time. Hopefully this time I don't mess them up though. And Josh, did I get it right this time? Yeah, okay. And let's see, let's work in green. So T is going to be the Earth, and T naught will be the isotope. Right? So again, you just like we did last problem, you substitute in. This time you're looking for V, right? If I remember. V, no. Oh, no, you're looking for T naught. So you can just substitute in, you're looking for T. And you have your good old 29 seconds over that square root of 1 minus 0.75 C over C, quantity squared. That's it. How does what? It has the speed as measured from an outside frame of reference.